So today in AC Electrical Circuits, we're looking at lab number 8, the series parallel RLC circuits. So under objective, this exercise examines the voltage and current relationships in series parallel RLC networks. It says often series parallel circuits may be analyzed along the lines of simpler series-only or parallel-only circuits. Both Kirchhoff's current law and Kirchhoff's voltage law are applied to these circuits, and we're going to record them both in the time domain and phasor plot of voltages and currents. The reference section refers to Sherman's Outlines, Basic Electricity, 2nd edition, and you can see we're going to be looking mostly at Chapter 18, and we're looking at the series parallel AC circuits. Under the theory overview, it says many complex RLC networks may be analyzed by reducing them to simpler series or parallel circuits. It says both Kirchhoff's current law and Kirchhoff's voltage law may still be satisfied for the entire circuit as well as any sub-circuits or branches. The equipment we're using today is the circuit test, SWF 7000, don't bother with its serial number. The oscilloscope will be the Tektronix. I'm going to be using the TDS 1002. And the digital multimeter, I'm going to use the Mastech MSM 9803. Now I've gone ahead and checked my components to make sure I have the correct ones. You can see my 1K is 995 ohms. My 10 millihenry inductor is 22.3 ohms. My 10 nanofarad capacitor came out to 13.45 nanofarads, and my 10 ohm resistor was 10.8 ohms. So in Sherman's outline, they have a nice section on series parallel AC circuits, and figure 18-7 shows you a series parallel circuit similar to what we're going to be working on today. So in Sherman's outline, you can see they've given us complete example of how to do the calculations for a series parallel circuit. Now I just want to bring to your attention that we do have to convert from polar or phasor form into rectangular form and then back again, so you might want to review lab number 2, phasors and vector review. We'll start the lab off in polar form, then we have to convert to rectangular form to add a complex angle together. So we're going to end up calculating something with an angle, and then we want to add another angle to it. So we have to change to rectangular form, and then to see it back on the oscilloscope with a phase angle, we convert back to polar form. So under procedure, step number 1, we're going to be using the figure 8-1. So originally this lab had 2 circuits, so I've just shortened it to 1. So we're going to have a 10 kilohertz sine wave at 10 volt peak to peak. So I've written that in. R1 is going to be 1K, L is 10 millihenries, and C is 10 nanofarads. So there's our 10 nanofarads, our 1K, our 10 millihenries. And we need to use that sensing resistor to get the phase angle of the current, so I've drawn that in for you, and that's going to be the 10 ohm resistor. So we need to determine the theoretical, inductive, and capacitive reactances, parallel branch reactance, and total circuit impedance, and record these results in table 8.1. We're going to then use Ohm's law and the voltage divider rule to compute the capacitor and inductor resistor voltages along with the input current and record them in table 8.2. So when you're looking at this circuit, it's really no different from a DC circuit when you go to solve it. R is in parallel with L. So this parallel branch is then in series with this capacitor. So we're going to get an angle for the capacitor. We're going to get another angle for the resistor inductor in parallel. And then we're going to get another angle for our total current going through the circuit. So before I show you the page of calculations, I just want to remind you that this is a series parallel circuit, and all we're going to do is try and find the total impedance or the total resistance of the circuit. So the resistance caused by the capacitance is XC, and it's going to be at an angle of minus 90 degrees. And remember, that's minus J 1 over 2 pi FC. The resistance generated by the inductor, XL, is at an angle of 90 degrees, and that comes from J 2 pi FL. Now, to start solving this particular circuit, we need to know what R in parallel with L is. And remember, to calculate R parallel, we can take the sum over the products, where R1 times R2 over R1 plus R2 is equal to our parallel resistance. The only difference between an AC circuit and a DC circuit is now we have to account for these angles. So R actually has an angle of 0 degrees, whereas XL has an angle of 90 degrees. So I'm now going to show you the calculations required to solve for this circuit. So the first step is to realize our component values. So R is 1 k ohms, C is 10 nanofarads, L is 10 millihenries. V in is going to be 10 volts peak to peak, and our frequency is going to be 10 kilohertz. So our first formula is for XC, which is equal to 1 over 2 pi FC. So that's going to be equal to 1 over, and I've put brackets around the entire thing, so if you're putting it in your calculator, you don't end up with 1/2 times pi. Okay, so it's 1 over this entire amount here, which is 2 times pi times 10k times 10 nanofarads, and that's going to be equal to 1.592 k ohms. And remember, this is an angle of minus 90 degrees. Calculating XL is equal to 2 pi FL, so that's equal to 2 times 3.14 times 10k times 10 milli. And that's going to be equal to 628.319 at an angle of 90 degrees. Keep in mind, our resistor value R is 1 k ohms at an angle of 0 degrees. The next step is to find Z parallel. That's of R in parallel with XL. That's the resistor in parallel with the inductor. We're going to ignore the internal resistance or the DC resistance of the inductor in this case. So what we're going to do is we're going to take R times XL divided by R plus XL. So you have to remember that we need the polar form of R times XL. So we take 1k at an angle of 0 degrees times 628.319 at an angle of 90 degrees, and that works out to 628.319 K at an angle of 90 degrees. Then to add the bottom portion, we're going to do that in the rectangular form. So R plus XL in the rectangular form is 1K plus 628.319 J. So that equals to 1K plus 628.319 J ohms. The next thing we need to do is convert R plus XL back to the polar form in order to do the division. So the magnitude is equal to the square root of the real component squared plus the imaginary component squared. So that's equal to the square root of, and in brackets to keep the two together underneath the square root sign, 1k squared plus 628.319 squared, and that's going to be equal to 1.181k. Then to find the phase angle, it's arctan of the imaginary component over the real component. So on your calculator, it's tan to the minus 1, bracket, 628.319 divided by 1k, close the bracket, and that equals to 32.142 degrees. So our answer, converting r plus xl to the polar form, is 1.181k at an angle of 32.142 degrees. Then finally, we can calculate z for the parallel part of the circuit as being r times xl. So r times xl from up here is 628.319k at an angle of 90 degrees, divided by r plus xl. So r plus xl in the polar form is 1.181k at an angle of 32.142 degrees. So that is equal to 532.023 ohms at an angle of 57.858 degrees. So moving on to calculate total impedance, so ZT is equal to XC plus R parallel. So that's equal to XC plus R in parallel with XL, which is equal to XC plus R times XL divided by R plus XL. So looking at our formula, ZT is equal to XC plus R parallel branch. When we're adding two phase angles together, it's easier to do it in the rectangular form. So our first step is going to be to convert XC to the rectangular form, and that's just minus JXC. So that's minus J 1.592k ohms. Then to convert the Z parallel branches, we need to take Z parallel and multiply it by the cosine of the angle. So that's 532.023 times cos of 57.858 degrees, and that works out to 283.047. So that's the real part of our expression. And then we're going to convert for the imaginary part of the expression, so we take 532.023 times the sine of 57.858 degrees, and that happens to equal to 450.481. So putting it together, we have 283 plus 450J. Then to do the calculation for Z total is equal to XC plus Z parallel branch. So you have your minus J 1.592k ohms, which is XC, plus the 283.047 plus the 450.481J. So that ends up being equal to 283.047, the real part, minus J 1.142k ohms. That's the imaginary part. So now we have to convert this back to the polar form. So the magnitude is equal to the square root of the real part squared plus the imaginary part squared. And that is equal to 1.177k. And then to get the angle, we take the arctan, or on your calculator, it'll be tan minus 1. And in brackets, remember, we need the minus sign from our Z total. So that's minus 1.142k divided by 283.047, and that works out to minus 76.08 degrees. So in the polar form, Z total is 1.177k ohms at an angle of minus 76.08 degrees. Now I just wanted to tell you that we had to convert back and forth from rectangular to polar form just to make it easier to do these calculations. But if you have the correct calculator, you can type this whole equation in, and the calculator will do all the conversions and give you the correct answer. So using your calculator, the first thing you're going to want to do is put it in complex mode. So press mode and your down arrow key, and then press 3 to put it in complex mode. You can see in my top corner here it's in rectangular form. So we're going to press second function, and then you're looking for a little arrow with an R theta. So in my case it's second function 8 key. And now you can see my calculator says R theta. So now I can type in my entire equation. So XC is equal to 1.592. Now this is K, so I press exponent 3. And then I press my angle key to put in the phase angle of 90, and then the plus minus sign to make it negative. To that I'm going to add, and in this case I want to add R times XL. So R is 1 exponent 3, and you can put in your angle of 0 degrees. We're going to multiply that by XL, which is 628.319, and that's at an angle of 90 degrees. Then we're going to divide it, and we're going to divide it by R plus XL. So to keep the order of operations correct, I'm going to put in a bracket, and R is 1 exponent 3, and it's at an angle of 0 degrees, plus I want XL, which is 628.319 at an angle of 90 degrees. And then I close my bracket and I press equal. And you can see it gives me 1.176 times 10 to the exponent of 3. And then when I press second function, EXP key, it tells me I have an angle of minus 76.074 degrees, which is what we calculated manually on our pre-lab calculations. Now to finish up our pre-lab calculations, we need to know what VLR is, or the voltage across the parallel branch. So we're just going to use voltage divider. So we just take Z parallel divided by Z total times the applied voltage. So in this case it's 532 at an angle of 57.8 degrees divided by 1.177 K at an angle of minus 76.08 degrees times our 10 volts peak to peak divided by 2 root 2 to get back to RMS value. So that ends up being equal to 4.52 volts peak to peak divided by 2 root 2 at an angle of 133.938 degrees. VC is equal to XC over Z total times your applied voltage. So in this case it's 1.592 K at an angle of minus 90 degrees divided by 1.177 K at an angle of minus 76.08 degrees times our applied voltage of 10 volts peak to peak divided by 2 root 2, and that equals 13.526 volts peak to peak divided by 2 root 2 at an angle of minus 13.92 degrees. Then finally, to calculate I total, it's equal to E total over Z total. So that's equal to 10 volts peak to peak divided by 2 root 2 times 1.177 K at an angle of minus 76.08 degrees. And that's equal to 8.496 milliamps peak to peak divided by 2 root 2 at an angle of 76.08 degrees. So in table 8.1, I've recorded my XC as 1.59 K ohms, XL is 628 ohms, R in parallel with XL is 532 ohms at an angle of 57.9 degrees. My Z magnitude is 1.18 K ohms, and my Z total is minus 76.1 degrees. Now you'll notice I've rounded these numbers up because I'm not going to get that much accuracy when I do the physical lab. On table 8.2, I've recorded my VLR, which is the parallel branch voltage, as 4.52 volts peak to peak at an angle of plus 134 degrees. Again, rounding those numbers up. VC is 13.52 volts peak to peak at an angle of minus 13.9 degrees. And my total current, or IN, is 8.5 milliamps peak to peak, and it's at an angle of plus 76.1 degrees. So under procedure, step number 2, we're going to build the circuit of figure 8.1 using R is equal to 1K, L is 10 millihenries, and C is 10 nanofarads. We're going to set the function generator to a 10 kilohertz sine wave at 10 volt peak to peak. And we're going to put the bandwidth limit on the oscilloscope just to reduce the noise and make for more accurate readings. I just wanted to refer you back to figure 8.1. We have our function generator that's connected to our capacitor. Our capacitor is connected to the resistor and inductor in parallel. Our inductor and resistor parallel branches come back and join at our sensing resistor. So this is the 10 ohm sensing resistor for us to measure IT, and that comes back to the common of the function generator. So going with a close-up of my circuit, you can see the red lead is going to come in from the function generator, and I'm also going to hook it up to channel 1 of my oscilloscope. It goes through this bus line to my capacitor, which is labeled 103, because that's a 10 nanofarad capacitor. The other leg of the capacitor joins the 1 k ohm resistor and the leg that goes to the inductor. On the other side of the inductor, I have a jumper wire because if you spread the inductor legs too far apart, they will break off the inductor. So at the bottom, my inductor does join back to the 1 k ohm resistor and also goes to the 10 ohm sensing resistor. The other side of the 10 ohm sensing resistor goes back to the common of the function generator. Right now I have a red lead from the oscilloscope channel 2 joining to the yellow lead here that's going across the 10 ohm sensing resistor. So under step 3 of the procedure, we're going to place probe 1 across the generator and probe 2 across the current sensing resistor, SR. We're going to measure the input current, both magnitude and phase, and record these in table 8.2. So looking at my oscilloscope, you can see I've set up channel 1. It's at 2 volts, and the bandwidth limit is on. Channel 2 is at 20 millivolts, and the bandwidth limit is on. So this bigger signal here is channel 1. The smaller signal that has a little bend into it is channel 2. And I've set up the measurements so that channel 1 frequency is approximately 10 kilohertz. Channel 1 is at approximately 10 volts peak to peak. And channel 2 looks like it's about 82.4 millivolts. So on table 8.2, I've recorded IN, experimental magnitude is 8.24 milliamps peak to peak. Remember, we read it on the oscilloscope as 82.4 millivolts. Dividing that by the 10 ohm sensing resistor gives us 8.24 milliamps. So to check my phase angle, I'm going to increase the sensitivity on channel 1 and on channel 2 and the seconds per division. And then I'm going to put my cursors on, and I need type time. So my first cursor is going to go through the first waveform zero crossing line, and remember that that is IT. And the second cursor will go through the channel 1 zero crossing line. Remember, that is V in. So this is V in. This is IT. So IT is leading, and it's leading by 20 microseconds. So in table 8.2, I've recorded my experimental delay as 20 microseconds. And to get the phase angle, I've taken 20 microseconds divided by the period of 100 microseconds times 360 degrees, and that is equal to 72 degrees. So continuing on in step 3 of the procedure, we're going to remove the sensing resistor, SR, and place probe 2 across the parallel inductor resistor branch. Then we're going to use the math function. The capacitor voltage can be found by subtracting the voltage of probe 2 from that of probe 1. We're going to measure the parallel branch voltage and capacitor voltage for both magnitude and phase and record these in table 8.2. So back here on my circuit, I've removed that 10 ohm sensing resistor and moved my common wire over so it's making contact with the bottom of the 1K and the green wire that goes to the bottom of my inductor. My sensing line, which goes to channel 2 of the oscilloscope, is now placed at the top of the 1K ohm resistor where it meets the inductor and the capacitor. So now I'm looking at the voltage across the resistor, inductor in parallel. So this waveform is V in, and you can see V in is at 10 kilohertz and 10 volts peak to peak. Channel 2 is the voltage across the resistor and inductor in parallel, and you can see its waveform is leading the input voltage, and it works out to 4.32 volts peak to peak. So I've adjusted my first cursor so it goes through the first waveform, which is the inductor and resistor in parallel. My second cursor goes through V in. So you can see my delta is 33.6 microseconds leading. So in table 8.2, for VLR, my experimental magnitude was 4.32 volts peak to peak. My experimental delay was 33.6 microseconds. Dividing the 33.6 microseconds divided by the period times 360 degrees works out to 121 degree phase angle. Now I want to look at the voltage across the capacitor. To do that, I press the Math menu button. The operation is going to be minus, and it's channel 1 minus channel 2. Remember, for both channel 1 and channel 2, the volts per division must be the same for the Math menu button to work. So you can see the capacitor voltage is larger than the input voltage. So in order to measure this, I'm going to turn off channel 2 by pressing the channel 2 menu button twice. And now you can see the voltage across the capacitor is lagging the input voltage, and it is larger. But I can't use the measure button on here, so I have to use the cursor button, and I need type voltage. So my first cursor is going to go to the bottom of the big waveform, which is VC. The second cursor is going to go to the top of the larger waveform. And you can see my delta is 13.4 volts. That's the voltage across the capacitor. To get the delay, I'm going to change the seconds per division to open up the waveform a bit. I'm going to try changing the sensitivity on the volts per division. And remember, if you change one, you have to change them both. So I've got both on 1 volt per division. Now I'm going to put my cursors on type time. Change the seconds per division to open up the waveform a little more. My first cursor is going to go through the first waveform, which is V in. And you want to get it right at the zero crossing line. The second cursor has to go through VC, which is the second waveform. And you want to get it right through the zero crossing. And you can see my delta is 4.9 microseconds, and it's lagging. So under table 8.2, for VC, I've filled in my experimental magnitude as 13.4 volts peak to peak. My delay was minus 4.9 microseconds. Dividing that by the period of 100 microseconds times 360 degrees worked out to minus 18 degrees. So under procedure, step number 4, we're to sketch the waveforms on oscilloscope plot 8.1. We're to display the voltage waveforms representing V in, V R in parallel with L, VC, and I in. And we're to use I in as your reference waveform. To draw your oscilloscope plot, I suggest you start with I in all by itself. So I've drawn in my I in, and I've labeled the wave as I in, and I had my oscilloscope set to 50 millivolts per division. Next, I recommend drawing in V in. And notice I've got it set to 2 volts per division. Now I've drawn my V in and labeled it V in, and it was at 2 volts per division. Now without moving V in back to the zero crossing line, I now have my channel 2 looking at V across R and L. So that's across the parallel circuit. So I've now drawn in VRL at 2 volts per division. Now using the math menu, operation minus channel 1 minus channel 2, you can see I now have VC on the screen, so I can sketch that in. So I've now sketched in VC, which is the largest of the waveforms. It'll probably look better if you use color pencils. So under procedure, step 5, we're going to compute the deviations between the theoretical and experimental values of table 8.2 and record the results in the final columns of table 8.2. So I'm going to leave you to do that. Then it says, based on the experimental values, determine the experimental total Z and parallel branch Z values via Ohm's law. So ZT equals V in over I in, and we're going to record those back in table 8.1 along with their deviations. So to find our experimental R in parallel with XL, we're going to take VLR and divide it by I in. So that's equal to 4.32 volts at an angle of 121 degrees, divided by 8.24 milli. Remember, that's times 10 to the minus 3 at an angle of 72 degrees, and that works out to 524.3 at an angle of 49 degrees. So you can see that this is off a little bit from our theory, and that's probably due to the internal resistance of our inductor, which was about 22 ohms. So calculating Z total, that will be equal to V in divided by I in. So that's equal to our 10 volts at an angle of 0 degrees, divided by our current of 8.24 milliamps at an angle of 72 degrees, and that works out to 1.214 K at an angle of minus 72 degrees. So it's close to our theory, but off a little bit, probably due to the internal resistance of our inductor. I'm going to leave you to calculate percent deviation. So under procedure, step number 6, we're to create a phasor plot showing V in, VLR, VC, and I in on plot 8.1. We're to use V in as our horizontal axes, and remember to convert all your readings to RMS before plotting the phasors. So on plot 8.1, to draw my phasor diagram, I first had to convert V in to RMS, so that's 3.536 volts. VLR to RMS is 1.527 volts. VC in RMS is 4.738 volts. And I in RMS is 2.913 milliamps. I've used V in as my zero line. Then I've drawn VC at minus 18 degrees, VLR at 121 degrees, and I in at 72 degrees. If you're wondering how I got these angles, I went out on the internet and printed a protractor so I could put it on my zero line and get all my angles that I needed to draw in my phasors. So the last page of the lab contains 4 questions for us to answer based on our results, calculations, and observations. And when you've completed your lab, show it to your instructor so that they may initial it to indicate that it is complete.